So yes, I'll be talking about uniformity testing when you have the source code. Hopefully by the end of my talk, at least the title will make sense. This is joint work with Robin Kothari and Ryan O'Donnell. And before anybody asks, there's no reason for that picture. It's not one of the authors or co-authors. It's just an Australian bird that I like. So I'd like to start with a disclaimer. So as usual, there's a disclaimer saying everything wrong that I'm going to say is my fault. Everything right is thanks to my co-authors. I'd like also to say thank you for the organizers of the conference. It's great to be here. It's also great to have access to a consistently good source of coffee, which brings me to the disclaimer. If I speak really fast, it's because I think it's roughly the 5th of the day at this point. So that might impact my ability to slow down. This is the outline of the talk. First, what is uniformity testing? After all, that's the main object of study in our paper. What does it mean to have the source code? What are our results? It'd be nice to get to that. And why are they not obvious? And finally, it's kind of nice to have results, but it's also nice when people can build on them. So the final question is what remains open? And well, spoiler alert, quite a lot. So please stay until the end if you want to see what you can do, and we couldn't. Also, other disclaimer, a lot of that is going to be my handwriting. I hope it's okay. I'll talk a lot, so that should make up for that. So what is uniformity testing? So I'm not going to give you a full story, but it's a statistics meets computer science task, essentially. So it's at the intersection of property testing, statistics, etc. And at its core, the question is, you've got some data over a known universe domain, discrete. You know the size k, so without loss of generality, the integers 1 to k. And you're given some small, let's say, distance parameter epsilon. You have some samples. I put the quotes here because that's going to change across the talk, from some unknown distribution p over that domain. So p is just your least favorite probability distribution on a domain of size k. And you ask that question, well, is p equal to u, the uniform distribution on the domain? Or is it at distance at least epsilon from u? So is it uniform, or is it like far from uniform? And you must be correct with probability 99%. So here are a few comments. U I'm going to use throughout to say this is the uniform distribution on the domain. Sometimes I'm going to say epsilon far. That means at distance at least epsilon from. I'm kind of lazy sometimes. And that probability of error, that probability of success 99%, which means probability of error 1%, you can see that as both the type 1 and type 2 errors. This is completely arbitrary, almost completely arbitrary. You can amplify that to any small delta at the price of paying a log 1 over delta by just repeating, standard majority vote. So this is uniformity testing. It's almost fully defined at this point, except for the fact that I haven't told you what far means, which seems like an oversight. So I'm going to get back to that in 2 slides. Just since, for most of my life, I'm very happy with this formulation, but data is never perfect. So even if it's uniform, there might be some imperfections. Ideally, we want something a bit stronger than that. We want to say that we're robust to a little bit of noise. So we still want to accept, the algorithm to accept when the distribution isn't quite uniform, but like close enough, ideally as a function of epsilon. So that's the goal. You accept things that are really close to uniform with like a bit of robustness, and when it's far from uniform, you say like that I'm pretty convinced this is not uniform. Now, before going to the definition of distance, why would you care about this question, except for the fact that it has been well studied, which is possibly the worst possible reason to study something. Well, here's one example. Someone comes to you saying, I've got this amazing thing I made, and I promise to you, it's actually it's a hash function. It's no collisions, it's uniformly distributed. And you might want to check that before, I don't know, deploying it in your favorite secure application. So that's one possible aspect. The other one, which generalizes uniformity a little bit, is just saying, well, I don't care about the uniform distribution, but I would like to know if this is what I have in my model. Like I've modeled this phenomenon as coming from I don't know, a Gumbel distribution or your favorite distribution, and you want to check whether this is equal to that reference distribution or far from it. So basically, instead of U, you put like some Q you know explicitly and you care about. Good news, if you can do uniformity, you can do that one as well, and roughly you lose some constant factors. So in that sense, the uniformity testing is complete for goodness of fit. One sample goodness of fit. Now, I'm going to actually tell you what the distance is. It is the total variation distance, also named statistical distance, which is defined this way. So the total variation distance between two probability distributions, ignoring some measurability issues and like et cetera, I think you can just take everything I say and like add measurable sets somewhere, and that becomes formally true. For the discrete case, we don't really care. So it's the maximum probability you have to distinguish between those two probability distributions. So over all possible events S, you take the difference of the probability put on S by P and the probability put on S by Q. And that difference is going to be your total variation distance. A nice cute fact is the fact that it's also equal to half the L1 distance between the two probability mass functions of the distributions. Another nice thing is, why would you care about this? It quantifies exactly, it's a tight characterization of how distinguishable two distributions are given one observation. So you have two distributions, P and Q. You get one observation, and you have got to decide which one of the two it is. That advantage is captured by total variation distance. Now, this is one of the things. This is our measure of interest for most of the talk, but we're going to want to have a little bit of robustness in our results and also use other things as a proxy. So there's also Hellinger distance that's going to appear, which you, since it's a quantum audience, you probably have seen in one way or another because it's directly related to fidelity. So if you take the quantum analog of Hellinger distance, then you have 1 minus fidelity, Hellinger squared, sorry. So the Hellinger distance is between those two distributions is some weird normalizing factor you don't really have to care about. And then you sum over all possible elements of the domain, and you take the square root of the difference of the square root of the density squared. Or more succinctly, it's basically the L2 distance between the square root of the PMFs. And another nice fact about this is it exactly quantifies how many samples are needed to distinguish two distributions with high constant probability of success. So before it was like one sample you've got to decide. This one is like you can take as many samples as you want to distinguish them with high probability. How many samples do you need? And the answer is up to constant factors, 1 over Hellinger squared. And finally, the third one we're going to see here is chi-square divergence. This one is not a distance, it's not a metric. It has that beautiful form, which is you sum over all elements of the domain, the square difference of the PMFs, and you normalize by one of them. So it's asymmetric. It measures some stuff. You can see it as an approximation to Kullback-Leibler divergence if you want. I don't particularly want to get into that right now, but it's going to appear as well. Now, a good thing about those things is they're related, at least, in one way. Actually, Hellinger and TV are related in two ways, but what we're going to use is the total variation distance is upper bounded up to constant factors by the Hellinger distance, and the Hellinger squared is upper bounded by the chi-square divergence. Another nice thing, since we're looking at uniformity testing, is the chi-square divergence with reference U is actually just the L2 distance between those things squared. Okay, I think that's all for like the preliminaries. Now, uniformity testing. Again, you have samples of some kind from some distribution P, and you want to check whether it's uniform or at distance epsilon far in total variation distance from uniform. The good news is we know the answer. And we know actually much more than that. There are like at least 2 parameters I haven't talked about, but square root k over epsilon square samples are necessary and sufficient classically. And the algorithm is also computationally efficient. I think there's even a work that looks at the exact constant in the big theta. So, you know, we've got that covered. Now you could have, since you know, we have this part covered and it says classically in the title, you might ask the same question, but quantumly. What if I had quantum capabilities and I wanted to solve the same question? What could I do? Well, it was information theoretics, so probably not a lot, at least not in its most naive way to phrase the thing, which is I just give you samples, classical samples, and like do whatever you want with them. That a quantum computer is not going to bring you that much for that. So that brings me to the part of the title that says source code, because that's nice, but there are many cases where we have a bit more than just IID samples coming up to us from the sky. Often, those samples are generated in some way. They come from a process, and we might want to test the property of that distribution that comes from that process, which was what I mentioned before with the hash function. Someone gives you a black box pretending it comes from a hash function. You can do something else than like look at amazement at that black box and hope for the best. You might have a bit more of a white box success. So, we can do something else if it comes, let's say, as a circuit, as just feeding random bits to it and see the output. We have the source code. I'm going to get back to that a little bit, but with my beautiful drawing capabilities, this is essentially what you could hope to do. So you preprocess that circuit. That you could just use it to generate samples, but why stop there? You efficiently preprocess it to get a slightly bigger circuit, but that allows you to do other things. And you could see how that allows you to bypass information theoretic lower bounds, just because in that model, even classically, you could just do some kind of brute force analysis of the circuit, open it, try to understand things. 0 samples maybe, but exponential time or worse than that. The question is, can we, in that setting, get something that is sample efficient? How many times do you need to run that new circuit you've created? And still maintaining fast preprocessing and fast execution. So more to the point, the access model we're going to assume is we've got access to a unitary that prepares that state corresponding to the distribution. So we've got a synthesizer for P that on input your favorite state will output that state, which is the superposition, square root of pi, I, and some garbage. And you also have access to those things. So you also have access to, well, UP, UP dagger, and control UP. It's a bit fastidious to write the P, but really that thing, that unitary, is the thing that prepares the distribution, that corresponds to the distribution. Before I go a bit further, I want to mention that the garbage here is really important. If you assume, you could assume other types of access model. If you assume one where like you get the same thing without the garbage, I claim that like your task is basically trivial. Because you know the uniform distribution, you could just test whether that's this thing, and in the no case, it's going to be far from it, so you can just do that with a number of executions that would only depend on epsilon. What makes it hard here is that you don't have access to the state without the garbage. So whenever I say with the source code, that's essentially what I assume. And this is what was known before for uniformity testing with quantum capabilities. So the first two results are in a slightly weaker because they assume they make a stronger assumption on the access model. Let's see if I get that right. But it was proven that you could actually do k to the 1/3 for testing uniformity in the quantum string oracle for constant epsilon. Already, this is kind of impressive because remember that classically you need square root of k. It's not hard to see, it's just a birthday paradox kind of thing. You need square root of k classically, and you already get a polynomial speedup. Then another work showed that you could like put back the epsilon in there because epsilon could be very small, showing k to the 1/3 over epsilon squared, which is still good, still better than classically, but it only improves on the k, not on the epsilon. And then more recent work by Jillian and Lee and Luo Wang and Lee showed that in a very specific regime when epsilon is really, really small, you could actually do square root k over epsilon. So in this case, it's kind of weird. You improve on the epsilon, but not on the k with respect to the classical aspect. And that was in the same model of having the source code. And our results essentially are, well, we improve on the first large regime where epsilon is anything from 1 to 1 over square root k. showing that we can get k to the 1/3 over epsilon to the 4/3. So we go from epsilon squared to epsilon to the 4/3. And we also retrieve, in an arguably simpler way, the square root k over epsilon bound for very small epsilon. We also have a giant regime, which does not make sense for total variation distance because total variation distance is always at most 1. But if you look at chi-square divergence, that could be very, very large. And we also have a tight bound for that one. So again, the large regime is when epsilon is between 1 over square root k and 1. And we show that you can, with k to the 1/3 of epsilon to the 4/3 uses of the code, test uniformity. And a small regime via a very simple algorithm I'm not going to mention really, you can actually do, again, the square root k over epsilon bound. You might notice these are only big O's. We also have a conjecture that it's optimal, and I'm going to get back to that in the open questions. All right. So in the rest, I'm going to focus on the large regime. And this is actually almost I think this is the formal statement, that we show, the full one. So there's an efficient algorithm which, in the large regime, so I'm reparameterizing things as theta, makes k to the 1/3 over theta to the 2/3 uses of the code for your distribution, and distinguishes between those two weird things. Instead of when P is uniform, I'm saying when the chi-square divergence between P and U is at most, I don't know, 0.99 theta, your parameter is theta, and also, you don't have too many big elements. So the maximum probability of any element is at most like, I don't know, 100 over k. Remember that for the uniform distribution, that would be 1 over k. So that you can tolerate that kind of noise. You can tolerate like some chi-square divergence from uniform, and also a little bit of, instead of being very totally flat, you're like kind of flattish. So that's the yes case. You have to say yes in that case. And in the other case, the no case, instead of total variation distance instead of total variation square distance at least epsilon squared, now I put like Hellinger squared at least theta. Think of theta as epsilon squared. This is a stronger statement because of that thing that I'm guessing nobody remembers. I barely remember it myself from a few slides ago, that relates total variation distance to Hellinger. But this thing directly implies the thing above, but is stronger in basically every single respect. Strictly stronger. So we want to prove this. And to prove that, we're going to build on a recent paper by my two co-authors, mean estimation when you have the source code. And again, if you don't care about uniformity testing, I mean, I hope you do, or like other generalization to an arbitrary reference distribution, etc., at least get that out of this talk. There is this very, very good hammer that you can use, and it's basically beta Chebyshev. So when you have the source code, you can do the mean, you can estimate the mean of a random variable with better than Chebyshev. Chebyshev would, let's see if that works. No, I'm not going to point at this. Chebyshev would give you a square root here. Square root n. This one just gives you n. So that seems like just, I forgot a symbol, but that makes a huge difference in practice. That gives you essentially a quadratic speedup for many things in terms of uses of the code or sample complexity. So this paper from 2023 basically gives the optimal statement for this. It builds up on some previous work. So there's a long line. You can look at that paper by Hassoudi and Magnier from 2019 for like a slightly weaker version. But we want to use this as a black box. We want to say, oh, I can use beta Chebyshev. That's my new tool in my toolbox. How do I use that to do uniformity testing? And intuitively, it seems pretty natural to just look at all the uniformity testing algorithms and be like, which one of them can be framed as a mean testing question? Which is good because there are, last time I counted, there was 7. With our paper that makes 8. There might be a 9th somewhere. So, it would be surprising if we couldn't use that. So let's try to find a uniformity testing algorithm that could be rephrased as I define a random variable, and then I estimate its mean, and based on the mean, I say yes or no. The bad news is, among those 7 algorithms, there was none that actually could be framed that way, so we had to design one that worked for this. But that's the general template. The recipe that we want to follow is we take n samples, and for us, they're actually going to be actual samples, IID samples in that first stage, phase 1, and you use them to somehow define a random variable y. So that new variable y will depend on the samples you took in that first stage. What you want from that is you want its expectation to be related to the chi-square distance between p and the uniform distribution, because that's the 2 cases you want to distinguish, right? One of them, it should be like less than 0.99 theta, and the other one, it should be at least theta. So you want the expectation of this thing to be this, and you also want it to have a small variance, because if y has small variance, then you can use Beta-Chebyshev and get the savings you want. Sigma is the standard deviation, so the variance would be the square of sigma. So that's step 1. If you come up with the right definition for y, and you prove those 2 things, then you're done, right? Phase 2, you use your quantum hammer, and you say, oh, no, I'm going to estimate the mean of this thing. I'm going to estimate expectation of y, and let's see what happens. And the last step would be to say, oh, I've taken n samples in phase 1. I've used the code m times in phase 2. What's the best way to balance the 2 so that the total sample complexity is minimized? So that's the template. So I'm going to refer to those as phase 1 and phase 2. Thanks. So that random variable we're going to define. So we take n samples. Let's xj denote the number of times you saw element j in those n samples. So the sum of the xj's is n. And renormalize things a little bit, define yj as this thing. The random variable will be, I pick j according to the distribution p, and I output yj. So the randomness will be j drawn from p, output yj. This is the random variable. So that's the thing for phase 1. And then we want to estimate mu, which is, well, the expectation when I take j according to p of yj. If I can do that, I'll be good, because it's not too hard. Like, this is a one-line computation to see that over the randomness of phase 1, the expectation of y is exactly the chi-square divergence I want. Here comes the issue. That mean mu is itself a random variable depending on the phase 1. So it's a purely classical random variable maybe, but it depends on those first n samples you took. So it's nice for it to have the right expectation, but it would be nice if it was also concentrated around its expectation with a small variance. Both the mean and the variance are random variables, so you have to analyze these things over the phase 1. So that phase 2, the quantum hammer mean estimation, could work. Bad news, it's actually not true, so it doesn't actually work easily. But morally, that's what we end up doing. There are a lot of additional technical details to show that, okay, it doesn't always concentrate around what it needs, but when it doesn't, it's actually helping us as well. And so when you put all that together, things turn out to give the right result. To do that, we actually need to do a lot of classical analysis for phase 1 to make sure that those 2 random variables, mu and sigma squared, actually do the right thing. And this is what we end up proving. So essentially, this is exactly what I said. When in case 1, when you are close to uniform, then the mean mu will be small and the variance will be small with high probability. And in case 2, when you're far, well, the mean mu will be large compared to the Ellinger square distance, and the variance will be small compared to what it should be, the mean, with high probability. And a lot of the technical aspect is to figure out what it means to be small enough and large enough for the mean and the variance. This is a purely classical analysis. This is the most technical part of there. There are some small lies I've littered all across this talk, so read the paper if you want to know what exactly is a bit more complicated than what I said. As a side effect, That also gives a new classical algorithm for uniformity testing. You can go through the same proof, and instead of the new quantum hammer for mean estimation, you can just use your good old Chebyshev, and that will also work. To conclude, okay, I've got 3 lines, but there's basically one big open problem I care the most about. So proving matching lower bounds. We don't have them. We tried. It's hard. If you have some ideas about how to prove them, please come talk to me. I'd be really happy to see final nail in the coffin of this. We have strong evidence, and we strongly believe it should be tight in all regimes. Another question is, can you use that quantum mean estimation hammer for other testing tasks? It seems very versatile. This is a beginning. Hopefully there is more. And that's all. Thank you. Also, no reason for the kangaroo.
We'll now take a few questions.
Yeah, thank you for the enthusiastic talk. So coming from classical information theoretic background, I was wondering if there are connections to the source codes known there, like Shannon codes and on. So do you mean, is there any connections?
No, so when I say code, I don't mean coding theory at all. I mean literally in the computer science, here's the code of the program, and I give it to you, and you can inspect it, kind of thing. As far as I'm aware, there is no connection to coding theory or Shannon theory there.
And you mentioned about the KL divergence.
Yes.
Why didn't you take that?
We don't use KL divergence. I just wanted to mention that as a reason for chi-square to exist. So if you do a first-order Taylor approximation to KL divergence, you will get the chi-square divergence. This is where it pops up.
So this garbage model, I'm not that familiar with it. You had, what, 3 properties? You had that it prepares a state with some noise, that it can be used as a control, and that you have access to the dagger, right?
Yeah.
Could you maybe point to which of those aspects are relevant to achieve this, or like why are these relevant to achieve this 1/3 improvement?
Okay, so this is essentially what you need to run that mean estimation algorithm. So the mean estimation algorithm that we use in phase 2 needs this to be implemented. The intuition for the 1/3, I guess it's just when you look at what you end up having in terms of the n you need for that lemma to get that stronger Chebyshev thing. This is just what happens by balancing things out. I guess you could have some intuition for the k to the 1/3 by looking at essentially finding a collision, which is the hard thing for uniformity testing. In the classical case, the square root k comes from the fact that until you see a collision, you have no information whether you're uniform over the full domain or like uniform on a random subset of size k/2. But in the quantum setting, finding a collision does not take square root k. So that doesn't tell you why that dependence on epsilon is what it should be, but at least that should give you some intuition about the exponent.
Thank you.